Question 9. This question is about compounds containing fluorine. Now I've got a shape of a molecule, krypton difluoride, KrF2. It wants the shape produced by KrF2 and suggesting a bond angle. Now krypton is in group 0, group 8. It's got 8 electrons in its outer shell. So 2 of them are bonded to F, so I've got 2 bonding pairs. And so of the 8 electrons, there are 6 remaining. So after the 8 electrons have had 2 involved in bonding pairs with the 2 Fs, then I've got 6 remaining. I've got 3 lone pairs. So I've got 3 lone pairs and 2 bonding pairs. So I've got 5 pairs in total. So it's you would think it wouldn't be planar. However, the 3 lone pairs will repel equally and as far apart as possible. So they will go into a trigonal planar shape in the middle. They will repel equally to a bond angle of 120. And then the 2 F2s, the 2 bonding pairs, will repel as far away from that plane of 3 as possible and go up and down. So it will produce something that looks like that. So the 3 lone pairs repel equally. Given between them there'll be an angle of 120. However, then the 2 Fs repel as far away from those 3 lone pairs as they can do and go up and down in a linear shape. Now when you consider the shape, then you don't involve the lone pairs. They influence the shape, but you actually don't see those. They're too small to see, and so it's a linear shape. You could draw it like that instead if you wanted to. Either way is acceptable for the mark, and the name of the shape is linear. Bond angle is 120 because you ignore the lone pairs when you consider the bond angle. A bond angle is only the angle between the bonding pairs. There are 2 lone pairs of electrons on the oxygen atom of a molecule of oxygen difluoride. Now oxygen's in group 6, so 6 electrons in its outer shell bonding 2 Fs, so there's 2 bonding pairs and there's 4 electrons left over after 2 of the 6 electrons have been involved in bonding pairs. So I've got 4 electrons left over, 2 lone pairs. I've got 2 lone pairs and 2 bonding pairs. So they'll go in a sort of tetrahedral shape, but when you consider the actual 2 bonding pairs, they're in a V shape and they're pushed closer together. So if you have a regular tetrahedral shape with 4 bonding pairs, the bond angle is 109.5 in something like methane, CH4. And then if you have something like ammonia, NH3, where you've got 1 lone pair and 3 bonding pairs, when a bonding pair is replaced by a lone pair, the bond angle comes down by 2.5, so it goes from 109.5 down to 107. And then when you replace another bonding pair with another lone pair, like in OF2 or in H2O, then the bond angle comes down by another 2.5 from 107 to 104.5. And the reason that happens is that the bond angle gets reduced and reduced and reduced, lower and lower and lower, is because lone pairs repel more than bonding pairs. So the lone pair to lone pair repulsion is greater than the lone pair to bonding pair repulsion, which is greater than the bonding pair to bonding pair repulsion. Silicon tetrafluoride SiF4 is a tetrahedral molecule. Deduce the type of intermolecular forces in SiF4. Well, silicon's in group 4, 4 bonding pairs, so all of its 4 outer electrons are involved in bonding. It's going to be a tetrahedral shape with a bond angle of 109.5. So it's completely symmetrical, 4 bonding pairs in a tetrahedral shape. So fluorine is more electronegative than silicon, so the fluorine is going to have a slight delta minus charge and the silicon is going to have a slight delta plus charge. However, there's no permanent dipole because it's completely symmetrical. All of those polar bonds, all the delta plus and delta minuses, cancel each other out, so there's no permanent dipole. So even though you'd expect it to have dipole-dipole bonding if there's electronegative atoms in there like Fs, it's not going to have any hydrogen bonding in there. There's no H to F or H to N to H to O, but it might have dipole-dipole bonding, or at least you'd think so, because of the Fs being electronegative, but it doesn't so because it's completely symmetrical, and so there's no permanent dipole. The delta plus and delta minuses cancel each other out, and so what's left? Van der Waals forces, the attraction between the electrons in one molecule and the protons of the in the nucleus of other atoms in another molecule.